So all I wanted to do is demonstrate some projects today, and the first one I want to show you is the latest Advent of Code project. By the way, the Advent of Code is coming. The Sans Holiday Hack Challenge is already up if you're into security. It's not particularly coding though, but Advent of Code is going to start on December 1. So I'll just mention that. This is where I get all these projects anyway. Although I wouldn't assign ones from this year. They don't want you releasing solutions during the contest. I don't know if it's a contest where you can win a prize, but anyway, they frown on releasing solutions while it's going on because it'll sort of spoil other people's fun. But you will be able to see brand new ones starting December 1, if you care. What we're doing now are ones from a couple of years ago. Anyway.
What language are they doing it in?
Any language you want. They just present the puzzle and people choose their language of choice. And there's GitHub repositories full of people doing it in every language you ever heard of. Python, Assembler, Java, C, everything. People often, a lot of coders in fact, practice a new language by doing Advent of Code.
I see.
I've always done them in Python just because I'm still working on my Python, but doing them in Assembler is pretty appealing too. Anyway, so the first thing I want to show you today is one I remembered from years ago, and I'm glad I finally got it working well enough for this. This one with pressure. Now, what this is, I remembered this. This is really a tree traversal project. There's another one like this earlier, and really quite appropriate for this class. So here's the kind of data you have to start with, and let me make this fit there better on these. Okay, so you have a tunnel, and the tunnel, you have a series of caves, and the caves are connected by tunnels, and there's a high pressure system in here, and there's too much pressure, the pressure is getting too high, and you want to release the pressure by opening valves that will release some pressure. That's the idea. So you have valves, you see are labeled AA through JJ, and each valve has a flow rate, which is how all the valves start closed, and it takes you 1 minute to open a valve, and it takes you 1 minute to go through a tunnel. And you only have 30 minutes, and you want to release the maximum pressure by the end of 30 minutes. So some of the valves have flow rate of 0, which means they're plugged, and even if you open them, it won't do any good. So those valves are useless to open, but the others have higher flow rates. So for example, here's one with 20. That would be pretty nice to open, but the problem is you can go straight from AA to DD. So just intuitively, it seems like that should be your first move. You can always start in AA, and the first thing you could do is go to DD and open this valve, and that would get a high pressure valve open quickly. And what happens is once you've opened it, every minute passes by releasing more pressure. So it'd be something like this. You move to DD, you open valve DD, now it's open, and every further minute it's going to release 20 pressure. So getting it open earlier is better than getting it open late, and opening one with a high pressure number is better than opening a low pressure number. And what you're trying to do is find the path that will release the most pressure by the end of 30 minutes. So anyway, I did this by stages. So here's the layout of the graph. This is essentially a graph. Here's the connections. And so the first thing is just find the paths. So you can go through tunnels to any of 3 valves, B, D, I, or B. You can see that here. You can go to D, I, or B in one hop. And there are 16 possible paths using 3 tunnels. And I just said find how many paths are there that pass through all 10 tunnels. How many possible paths? And that's, of course, the first thing. One simple brute force technique would be to enumerate all possible paths and then try them one by one, unless you can find some way to lower that number of things you have to explore. And if every path was connected to every other path, it would be 10 factorial, which is a really big number, but it's not that big because the tunnels are only connected to a few others. So anyway, that's the first bit of exploring the spaces, deciding how many possible paths there are through this stuff. Now, next thing is to notice how you can simplify the problem. First, consider just find the shortest path from one valve to another. So if I want to go from AA to AA, that's 0 tunnels, that's going nowhere. If I want to go from A to B, that uses 1 tunnel. If you go up here, you'll see A has a connection directly to B. So I just have to go through 1 tunnel. But if I want to go from A to C, it doesn't have a connection directly to C. So I could go to B and then to C, and that would be 2 tunnels, and nothing's going to be shorter than that. If I want to go to D, 1 tunnel will do it. If I want to go to E, it looks like I have to go to B and then C. Now I got to get D. I can go to D and then E. It'll go to D, and D has a connection to E. So again, I could do it in 2 hops. So you can find the shortest possible path to everything. And you see one of them is pretty long, but most of them are pretty short. And so then you can find the shortest route that hits every valve in order, A through J. And some other valves will have to be visited more than once on the way there. That's another way to just see as you traverse the graph. And the next one is probably the most important step of progress, which is to realize, if you think about this, these tunnels with flow rate of 0 are useless. There's no reason to open that valve, and therefore if you think about it, all that really matters is to make it to the open valves and open them. So rather than saying, I have a valve here with flow rate of 0, and we're going to pass through it, you might as well say the only reason to ever go through a place like FF or GG is on the way to something you can open. So so what you can do is you can simplify the graph by removing all the ones with flow rate of 0, except AA, which is the first one, and you can now talk about a fast route. So I can go to, the question is, how many minutes will it take me to go from to the 2 and then open the valve? I can go from A to B in 1 minute, I can open the valve in 1 minute, so in 2 minutes I can open B. And you figure out how long it's taking. You'll find now instead of having 10 valves, 10 locations, you only have 6 to locations and 7 from locations. So you simplify the graph. This takes the graph from something with 10 caves and a bunch of tunnels to only 6 caves and a bunch of tunnels, which is much smaller. And it still is mathematically identical to the previous one. So, the zoom is failing again. When I zoom in, it doesn't zoom in the zoom. Oh, it scrolls anyway. All right, that's weird. Okay, anyway, all right, so that's the next thing. Now there's a bit of data you can use, the official data, which is a much bigger array of tunnels. This is something like 15 or 20 or 25 tunnels located here. So this is the one you're actually going to solve, the more complicated array. And this one you clearly want to reduce. So simplify this one. Create the simplified graph, and if you just add up all the minute values, you'll get a flag to turn in. So that's one way to make the problem easier. And once you've got all that, now you can solve the original fundamental problem. So here's the best procedure. Race to a closed valve with a non-zero flow rate using the shortest path and open it. Then race to another closed valve with a non-zero flow rate and open it, and keep going until time runs out or all the valves are open. This is obviously the way to win. It's going to be something like this. Wasting time going to a valve that's already open is useless. Going to places with flow rate of 0 as a destination is useless. This is clearly the efficient procedure. Will obey this. So the only relevant decision is what order to visit the closed valves in. And here's the order that's best: A, D, B, J, H, E, C. And when I wrote my code this time, I got this kind of output. However, the first time I followed the instructions and I actually created this minute by minute and tried every option. But this, we'll see it. This is how it shows you how it's going to work. And you can see the total amount of pressure released adds up is 1,651. That's all these numbers added together. So anyway, so this is the example where they give you the right answer and the step-by-step way to calculate it, so you can see if you figured out the best route. And then, of course, your challenge is to find the best route for that bigger network, this bigger network. And one thing I did that helped a lot, this grew to a huge number, too many to explore. But then I realized if I terminate each path when it has used up the 30 minutes, that prevents the number of paths from growing too large, and ends up there's only about 100,000 possible paths through the reduced graph that only consume 30 minutes. And 100,000 is not too many for Python to go through in a few seconds. So this, I think it took me about 30 seconds to do this after I optimized my code. So that was good. And the next part is considerably harder, and it goes like this. What if you have an assistant to help you? Now there's going to be 2 of you running around opening the valves, but it takes 4 minutes to train the assistant. So you don't even start until you only have 26 minutes left. So you lose some time, but you get some help. And so the question is that worth it or not? And in order to answer it, you have to say, what's the total pressure you could possibly use with the assistant? This turned out to be a lot harder. And so here's the example for the simple case. It's AJ, BC for me, and ADHE for the assistant. That's the one that does it, that releases the most. Now remember, previously it was 1,651 up here, was the total pressure released. With the help of the assistant, I get to leave 1,707. So it is a larger number. So the assistant does improve things by somewhat, but solving this is pretty difficult, and there's a lot of procedures, I'm sure. What I did was I realized that the 2 are pretty independent, and so I've just made all possible paths for a single person up to a certain number of nodes. And then I realized the other thing I realized is if I have a series of nodes, I do not need to try all permutations of this series. There is one best order in which to visit these for, and there's no reason to ever use anything other than the best order, because if you visit them in a different order, that doesn't affect the assistant at all. So if you consider all possible permutations, it's too many to explore. But if you optimize each one and only remember the best one for each combination of valves, then it gets down to a reasonable number. So you have to get all the possible paths of U, and the assistant's job is a simpler task because it can skip all the ones that you've already opened. So it's got a smaller graph to hunt through. And so I was able to get one. It still took about a half hour to calculate in Google Colab. In fact, I think it was so slow in Google Colab, I got fed up and I ran it on this Mac M1, which is faster. And there it was maybe like 10 minutes. And I'm sure there are probably smarter ways to trim it, but it took me a while. This was pretty difficult to figure out the optimal path. Anyway, I found it very interesting, very challenging, and I recommend it. Of course, as I mentioned before, if you're not doing well, you're just trying to get points, then just go through the projects and do the easy ones. That's the fastest way to get points. But these hard ones are good if you want to get practice doing the stuff we're really talking about, like complicated structures. That's a complicated graph, and you're figuring out how to traverse it and how to make sure you've hit every possible path, which is an interesting challenge and quite useful. Good afternoon, water skater. All right, so that's what I wanted to say about VP39. Let me stop that one.